13th question, that has been derived from the topic atom, which is in modern physics. And this is something to do with the atomic transition from excited to ground. You see, there is a He plus ion, and in the process of transition from excited to ground, this emits this wavelength and this wavelength. These are the wavelengths which have been emitted. And we need to calculate the initial quantum state, the state when it was in the excited one. Let's do one thing. This particular conversion has been given, so this is a smarter way to calculate the energy in electron volt. It's simply the product of Hc. You must have certainly used it in your practice phase. So here what I get is, let me first calculate the energy gap corresponding to these transitions. So that will give me 1240 divided by 108.5 plus 1240 divided by 30.4. Okay, so this will give me the energy gap corresponding to the transition. So it's something like this, see. This is the energy of the nth state, this is the energy of the first state, and there goes the energy gap that we have calculated. So therefore, what you can write is, say, minus 13.6 into z square divided by n square, n is 1, will give me the energy of the first state, plus delta E, the energy gap that I have calculated, will lead me to the nth state, and that is minus 13.6 z square divided by n square. So that is the straightforward one, though the calculation is a bit messy, but we can easily solve it. You do that, you will get the value of n as 5, and if n is 5, first option has to be the correct one. Let's move to the next. 14th question. The figure is a bit lengthier, but if you go step by step, it's quite a simple one. It says the figure shows a square loop L. The square loop, this one has been called as L, of side 5 centimeter. That means the length has been given. And this is connected to a network of resistor, and it's so visibly clear. There is a Wheatstone balance bridge lying out there. And this thing is being pulled with a speed of 1 centimeter per second. The magnetic field has been given 1 Tesla, and the resistance of the entire loop L has been given 1.7 ohm. We need to calculate the current in the loop at this instant. So, you know, the question is being framed by adding 2 or more different concepts together, but they are the regular feature. Like this is the motional EMF, there you need to put the Wheatstone bridge. All right, so here if I calculate the Wheatstone bridge, you see this one will be off since it's the bridge, and now it's so easy. 1 and 1, 2, and 2 and 2, 4, they are in parallel. So 2 and 4 parallel, that will be 8 by 6, which is 4 by 3, and 4 by 3 will be in series with this. So what we get is R equivalent, that's, I'll repeat it again, this is 4, this is 2, so 4 and 2 parallel will be 8 by 6, which is 4 by 3, and that is in series with this. I think we can go in this way. 4 by 3 is very close to 1.3, and 1.3 in series with 1.7, the equivalent resistance is 3 ohm. That has been done. The equivalent resistance of the entire circuit has been calculated. And with the concept of motional EMF, this one is not producing any EMF, neither is this. It's only this which is producing the EMF, and that is BLV, okay? So I can calculate the current, and that will be BLV divided by the net resistance, which is the equivalent resistance. And after we did this, the value of current that you calculate would be 170 microampere. Be a bit careful in terms of unit. You need to keep that presence of mind. And if 170 microampere is the answer, first option has to be the correct one. Fine, let's move to the next. Proceeding forward, question number 15. Now, this requires a bit of calculation, and it says there is a uniform rod of length L which is being rotated in a horizontal plane with a constant angular speed about an axis passing through one of its ends. And we need to calculate the tension as a function of distance x from one end, and that end is of course the center. And apart from calculating, we need to plot the variation of tension with respect to x. So these are the four options among which we are going to choose the option which matches the best. Okay, let's take the help of a figure here, and it's something like this. This is the rod, and let's say that the rod is revolving around this given axis. Let me just try to show it with the help of a figure. Yes, so this is the axis around which the rod is revolving. And I need to calculate the tension at a distance x. There can be many different ways, and one preferable way is that you go and you start going with the integration technique. But this time, let me go with something a different way. Not a very peculiar, a regular one that you can do. So at a distance x here. So I'll be taking this as the system. And if I take this particular thing as the system, the tension acting here will be acting as the centripetal. And for this, the center of mass of this can be taken. So that is the experience you need to carry, that while you analyze this thing, the center of mass of this element can be treated in the revolution part, but not everywhere you can, replace by the center of mass. You need to have the validity, and this is all by experience. Okay, after all, you've taken 2 years to come up in this given thing. So what we'll do is see the tension here will be equals to this much of mass, if you see, is m by L multiplied by L minus of x is the mass, into omega square, and here is the center. So that will be x plus L minus of x by 2. I think that's straightforward, right? X plus remaining half. And just try to see here, this is 2x, and that's going to be L plus x, L plus x, L minus x. Eventually, the tension here you would be getting would be directly proportional to L square minus x square. That much is more than sufficient to plot the tension, and this is a downward parabola, right? Tension versus x square. So what you could say is that the downward parabola means option number 3 would be the correct option matching for this given situation. Let's move to the next one.